Let's just start this podcast out by saying I'm not really sure what we call this podcast anymore. There are a variety of possible options, I thought, at this stage, particularly because if you rebrand a podcast now, I mean, there are so many beautiful options like Save a Life Podcast or maybe Get a Life Podcast. But I think probably for now, at least, we're going to stick with the Biota podcast. I'd like to welcome back on Anton Mikhailov. Anton, you emailed me at the end of last year, just as literally in the day, I think, of that I was about to fly to Australia, saying that you wanted to have a chat, you wanted to have a recorded chat about parallelism. And I thought this was a wonderful opportunity to start the new year and talk about our various musings. In my case, a summer project that I worked on over the Australian summer, at least. And
oh, right, yeah.
When we last spoke, you were getting very heavily involved with a project that had a long heritage and connections to YouTube. Are you still working on that project? Are you still adding things, or have you moved in a different direction?
Well, I ran into a bit of a roadblock there. That was, porting the Moveable Feast Machine to the GPU. And the problem is, so I got a good way there and it was simulating quite large grids. But I actually started crashing the compiler, the shader compiler for the GPU. And so that kind of opened a can of worms. And then I happened to know some friends that know people at NVIDIA and AMD and Google and stuff, the people that write the compilers, and I sent them the shader and they're like, oh, Jesus, this is crazy. And so it actually apparently unearthed some ancient compiler bugs because it's sort of at the limit of what GPUs were, designed to do reasonably. We were taking it quite off at this point. And so we ended up working through it. I rewrote the whole thing on top of Vulkan instead of OpenGL because OpenGL apparently is dying out and the compilers are getting old and
certainly
rusty. So anyway, I rewrote the whole thing in Vulkan and it does work now and it does compile, but depending on the actual simulation, it takes between 5 and 10 minutes to compile the shader alone, which is also a bit crazy. So it sounds like there's some kind of some sort of inefficiency inside the compiler dealing with the very non-standard code I'm throwing at it. Seems to be pointing at like register allocation or something. But anyway, the whole point of the project was to have kind of fast iteration times because you can do this sort of hot reloading stuff where you just change stuff and then, you're running the sim right away.
Certainly.
And so, that works, provided you don't sort of layer it too thick. But of course you want to layer it thick because that's the only reason you want to do this, hot reloading. Because simple stuff, you kind of can guess what it does a lot of the time. But it's trying to develop the more complex stuff. So anyway, it's a bit on ice right now. We have some open bugs with Google and NVIDIA trying to, obviously low priority, but some kind of eager people are digging and seeing if, is it possible to actually make this thing compile quickly? It runs very fast once it compiles, but it seems like there's some kind of, n squared or n cubed or worse thing happening inside the compiler, probably during the optimization stage, making it unusable. But once that's fixed, I think I'll kind of come back to it. But so having hit that roadblock, about a month before the holidays or something, I was a bit working, but it was a bit disheartening, especially after porting the whole thing, still not, kind of getting a small win, but then not a big win. So I thought, okay, I'm just going to hack on my own A-Live stuff just for fun and try to stay away from crazy GPU stuff and just do simple CPU things and see where I can get to. And that's kind of why I emailed you because I thought, okay, well, I've got some ideas that I want to try out. But yeah, like I mentioned in the mail, I've never gotten things to parallelize well. So instead of trying to deal with GPU parallelization, I thought, okay, well, I'll deal with CPU parallelization. At least that's a sort of a less crazy devil, I think. So anyway, that was the genesis of my mails, to sort of relax and do some non-GPU work just to clear my head a bit. So.
Well, my word on that is non-blocking synchronization. I think that's the easiest way to explore artificial life and parallelism without getting caught on a series of roadblocks. And thankfully, because a lot of the nature of A-Life simulation is to do with information flows anyway, you get good direction and you can avoid locking, basically, certain parts of the simulation. That being said, it is a really fascinating way to write code. And my experience was in part sparked off by Apple and Intel's use of my simulation, but also once I saw how the folks at Intel were doing it, and we're talking probably about maybe 10 engineers over a period of time, I realized that there were a series of ideas that I could implement, things like atomic processing and just the way I structure the code. And then later, through my day job, I met a fellow who was like a guru in functional programming. I think he's now at Facebook. He went from Yahoo, Microsoft, Netflix, Facebook. I think that was the trajectory. So I knew him in his Netflix guys, and he, although he wasn't interested in simulation at all, the way he evangelized, large scale information processing through functional programming just made me realize that you get parallelism for free if you implement proper functional programming methods. And so I rewrote my simulation at the time using that stuff and was able to scale very easily and not hit any of the standard roadblocks or bottlenecks that most people talk about. So, I mean, I think I've come to it through a variety of different sources, and now, particularly working on the iOS implementation, I've moved back from the functional programming aspect because I'm really returning to, one, two, well, probably two, three thread models at the most, because of the way the CPU engages with battery. And so I'm moving in a different direction there, but at the same point, these experiences teach you new ways of looking at simulation, new ways of dissecting simulation, new ways of, certainly with my own, what is now called the ApeSDK, it's a series of simulations that are designed to be run effectively in parallel, and certainly if not explicitly in parallel, at least, atomically cut in parallel. But it's an interesting discipline to get into in the context of you have an existing simulation idea, maybe some depth. I mean, your B stuff lends itself very heavily to this kind of this kind of means of processing. But yeah, it is interesting. I mean, if I can give my little bit of news, my summer project for the 2 weeks that I was in Australia was taking a project called libdeep. Now, I'm really fascinated in the kind of, I don't know even if it's a juxtaposition or the history of machine learning in artificial life. That's a new thing that I'm on. And how much of machine learning actually required concepts in artificial life, and how many of the basic concepts of machine learning, like, is there a history where artificial life is critical for machine learning, or is there a history where artificial life is just built on the same building blocks that machine learning is built on? With the view that increasingly, both on the lower, Android devices, iOS devices, what have you, they now have relatively robust machine learning, libraries, at least associated with the low end. And then you've got things like TensorFlow and all this other stuff, which is doing the kind of cloud machine learning component. So in this sandwich of ideas, my friend Bob Mottram, who contributed heavily to my simulation from about 2011 through to about 2014, 2013, after he'd worked on my stuff, he created a machine learning library called libdeep, which was designed to teach machine learning concepts to novices in very robust C code. And it really is a thing of beauty because it enables you to create a variety. I mean, it's a bit like TensorFlow, but not like TensorFlow. It's a kind of curious thing that you can create all these kind of experiments, but then you can output directly real, floating point math that does the calculations after the fact. So it's a fascinating project, which unfortunately Bob's kind of, I don't know how one would call him. He's like one of these jazz kind of artist that moves around from project to project. So he left it in one state, but I thought this could be so much more. And I have obviously a long-term legacy working with Bob historically. So I'm like, I'm going to take this project of Bob's and make it work universally. There were various issues within it, and add a bunch of continuous integration tools because I'm fascinated by that simulation stuff anyway. My own project, what that work did was now I have every commit to the ApeSDK runs the simulated apes, as they're called now, for 1,250 years of different simulations. So each time you commit, you get this huge, amount of data. And I'm really fascinated by how all the advances in continuous integration tools really help artificial life projects as well. My summer, which was from late December to early January, was spent rewriting libdeep, fixing a bunch of stuff, make it universal, removing it from the very kind of Linux-centric perspective that Bob had at it, and making it code that is completely generalized now and can run on whatever platform you want to throw it on. But through that, I realized that the success, because, I mean, Bob really didn't have a lot of success when he was working on the ApeSDK. I mean, I loved his work, and I thought his work was amazing, but it didn't get like, you know, he wasn't having tens of thousands of downloads and lots of stars on GitHub and all this other kind of stuff. When he did libdeep, he started getting that crazy open source kudos status, which I think his work deserves anyway. And it just fascinated me about, like, what I do and what libdeep was. Like, what's the distinction in terms of getting a lot of people? Well, obviously, you know, machine learning is the latest thing in terms of you need to have it on your CV if you want to work at whatever they call it, FANG now or whatever. So, I mean, I think, and certainly in our community, folks such as Larry Yeager, I mean, Larry Yeager basically, and a wide variety of other folk that we've talked to in this podcast, have been really seminal in important parts of machine learning. So the relationship, and part of this came through, what do they call it? It's not Stack Overflow, but it's connected to Stack Overflow. There was a post recently that what I call a peacock post. A peacock post is a post where the person who's posting wants to make the widest possible spread, but wants to have the least possible, like, direct positive impact. And so this person posted saying, you're like, what's the history of artificial life? Like, why is it lamenting? Why is there no commercial success? And my view is, okay, take machine learning, and I own a Roomba. I wouldn't necessarily say iRobot is the pinnacle of artificial life, but at least Rodney Brooks has some history in the field, and, you know, it's a commercial company. So you want to point out commercial things that have come from artificial life. I think good portions of machine learning have solid crossovers in artificial life, and let's just talk about iRobot as a thing. So, yeah, I responded.
Yeah, and they just made that little biology robot or biology thing out of frog heart cells. Did you see that thing?
Yeah. No, I mean, look, the whole history of Rodney Brooks is amazing. So, yeah.
Yeah, no, I mean, I guess it's just, I do kind of, you know, there is a dose of truth in that sort of question in the sense that it doesn't feel so much like artificial life because you don't have, you know, the Roomba doesn't seem like it's a dog or a cat, you know, it feels like a robot. And I think when people see artificial life videos, like whether it's, you know, Noble Ape or something else, that they're imagining these worlds and these.
It's called the Ape.
Oh, it's not called that anymore.
It's no, believe me, that is no longer affiliated with Tom Barbalet. Let's just move on from that. But look, let's talk about the Roomba. My view is that the Roomba, as it exists in public consciousness, is associated with the cat riding on the Roomba. I mean, that's the id of the Roomba, is this notion. And when we got our Roomba, I named it after one of our deceased cats. I mean, my view is that actually the Roomba exists in cat. It was interesting, actually, because our cats, we have 4 of the creatures, really wanted to break the Roomba in. Clearly, the Roomba thought it was an alpha cat, and the rest of the cats, particularly our major alpha, he did things like he cornered the Roomba and then he fell asleep. So the Roomba was completely blocked and couldn't move. And he did this over maybe 3 or 4 days, which was literally jumping the Roomba into our cat tribe. Like, oh, you think you're the alpha cat? No, let me show you. So my perspective actually on the Roomba is, I mean, certainly amongst our cats, it was seen as being an entity that was encroaching on their space. And obviously we named it after a deceased cat. And I think in terms of the public consciousness of the Roomba, the cat riding on the Roomba is it. What say you, Anton?
Yeah, but it doesn't have legs, you know?
Well, most of my cats don't have legs. Like functionally have legs. But I mean, I think in terms of its movement and in terms of its characteristics, I mean, if you could approximate all things to dots, basically. If you approximate it to a dot, then it has cat-like behaviors.
Right. Yeah, I think that's kind of the naive, you know, obviously it's a bit facetious to say it doesn't have legs, but like there's something to the fact that I don't think it has crossed that sort of that valley where you think, oh, that thing appears alive. It still appears quite automatic and stuff. It does have moments where it sort of does something funky and you're like, oh, it's a bit cute. But there's an overall stupidity that I think isn't present in cats.
Well, maybe you haven't owned enough cats. I guess my
Perhaps.
they have the I Create too, which is something that I certainly, as I've owned the Roomba for longer, I thought I really wish I could hack this thing because, quite frankly, it, as you say, it does a bunch of stupid stuff, and ours certainly functions about a third of the time correctly. Again, very cat-like. So, I mean, my perspective on it is that it would be a very interesting project to start hacking the I Create 2, which I think is about $200 from memory. And it's basically the third generation of the Roomba or the fourth generation of the Roomba without the brushes, although there's plenty of hacking videos about installing the brushes. And you can program it through a relatively simple operating system, like very, straightforward kind of binary components to it. But it fascinated me. I mean, I obviously haven't purchased one of these things. I'm kind of trying to reduce my hobbies, not increase them. But I often wondered what it would be like if I put the ApeSDK on one of these things and let it productively learn our house versus the way the Roomba obviously has. And I think the other thing that I've noticed with the Roomba, having had it, although this shouldn't necessarily just be a Roomba podcast, is that the battery life it really doesn't have a very good knowledge of. And I think the kind of centrics that I'd want to see in A-Life programming around the Roomba, it's certainly missing a number of those components. And I'm looking to work more with roboticists, I think, in the next, as we're in a new decade as well. Let's run all the cliches here, Anton. I'd like to work with roboticists more because I think they probably hold some of the elements of taking the stuff that, maybe we as a collective have done in a different direction. That's what I really find inspiring with Rodney Brooks's work.
Right.
Is that he...
that's his whole... Yeah. That's the whole piece of, embodiment in the world being a key part of it. There is also some truth to the congealing of A-Life people. Like, you have Brooks and then you have, like Steve Grand who had a studio. But then other than that, it's hard to name like sort of A-Life focused groups of people. Like you can sort of, it seems like when people do A-Life work, it's quite solitary. So maybe that's
I think that's artificial. I think there are certainly academics that are, I spent an amount of time at Michigan State University. They've got a good school there that's turning out interesting A-Life people, many of whom, end up in the San Francisco Bay Area. And I think also if you look at what happened, and unfortunately I can't remember the gentlemen's names, but is it Kenneth Stanley? We had him on. And what's the other gentleman? They are now... I don't know what one would call them, like associate professors at Uber, and I'm assuming that they're working on the self-driving car stuff. So, I think there are a lot of names in the community, many of whom I've had the opportunity and the pleasure of talking with on this podcast, who do work heavily in industry. The whole notion of what's like fame and importance and, Steve Jobs and all those other kinds of things. It's very convoluted. I think the nature of artificial life as a discipline is it's gone in a variety of different directions through a wide number of individuals. And the notion that what we need here is, I guess, Elon Musk-like characters, I guess. They can just say, well, I'm the artificial life dude. I just don't see that as being what's happened here. I think what's happened here is there's been a series of, academics and industry types and a few hobbyists as well. And we've all continued on with particular passions, and this technology's gone a variety of different directions. I think the need to kind of catalog and describe this, I've tried to do through this podcast. And certainly if you look at the International Society of Artificial Life, they've tried to do it in their own way. Now you've got Gecko, in a conference series, you've got IEEE through conferences trying to do it. But I don't think the general public necessarily needs to know that Larry Yeager, worked at Apple, worked at Indiana State, now works at Google. This means that Larry Yeager's technologies from the Newton through to, whatever he's working on at Google. That strikes me as a really curious narrative. And the nature of peacocking, which has existed the entire time I've been developing artificial life software, is just that you'll always have some guy who's read something that likes to post on a forum somewhere saying, well, gee, what's happening with artificial life? Well, maybe get in contact. He listed that he had looked at a number of projects. He'd found the source code for my stuff and a variety of other folks' stuff, and yet he never got in contact with anyone. He just posted on a
Yeah,
whatever.
I certainly don't like condone the tone of the post, and like you said, it's like strangely inviting to it's not the right vibe for sure. I think part of the issue is that the term like A life is so broad, like almost even broader than artificial intelligence, because at least with artificial intelligence, you can kind of imagine that it's trying to do some reasoning or whatever you want to call it. That's broad enough as it is, but when you have things like robotics under the same umbrella as like cellular automata, that's like such a sweeping term for A life that, like you said, it's applicable in so many random different areas that there's not going to be, like you said, some sort of Steve Jobs moment where they say, the whole of artificial life has now been applied to this one problem and it's been solved. And like you said, actually, Roomba is probably the most sort of cohesive argument you can say, like, but sadly, it hasn't solved vacuuming. Like, if you were to truly solve vacuuming in a deep way, then at least you can claim artificial life has solved vacuuming in a way that I think, artificial intelligence, or I guess, deep learning in the current sense, has to some extent solved like character recognition. Like, obviously not driving, but for a large percentage of tasks, like it has quite, I think, successfully solved basic computer vision tasks. Not quite as hyped up as it tends to be, but I think, the idea that you could sort of train a machine learning model to recognize like beer cans or something would have been a really massive undertaking 10 years ago. And now it's like, you can just read a little tutorial and you'll have something in a day or something. Maybe it won't be worthy of a factory line, but it'll get you like 90% accuracy for something that would have been considered like, a PhD level task a bit ago. So I don't know if that means.
I mean, my perspective is, I first saw neural networks in the mid-'80s. There were neural networks, simple neural networks, but I first saw neural networks in the mid-'80s. It was pretty clear that these things would recognize faces relatively quickly based on processing. And I think the nature of machine learning problems, I'd love to talk to someone like Larry Yeager about this as well, because, I mean, Larry Yeager was actually there at certain points of this journey as well. Once you understand distributed processing to a certain extent, you can see, this problem will be solved just by raw computation. And I think that's what machine learning has done very successfully. It's just taken problems which we knew were going to be solved by computation, and wow, we've got computation now, and wow, these things are solved. And I think what's interesting to me, particularly when you look at the Venn of what from artificial life, what the building blocks of artificial life are in machine learning, what in the building blocks of artificial life aren't yet in machine learning, that is something that I think is really fascinating, because this is an area where I look at, okay, how much of the ApeSDK can I move into Apple's machine learning library? Okay, well, this much. Well, what about the rest? Well, okay, so there's some agent modeling where I can get some optimization, okay. But there's still at least half, if not 2/3, that don't exist in any of these paradigms and actually are really fascinating ways of understanding organic problems. So I think what's interesting in the field currently is not just what has been used elsewhere, but what is still there potentially to be used in, new solutions for a variety of problems. And I think certainly as we have a certain number of kind of undergraduates that listen to this. I know it sounds scary, but we do. And my thought with these people is think about the future problem space, not in terms of what has been solved so far, but what exists. I mean, I think of artificial life in some regard like the Amazon, right? The old metaphor of the Amazon that the cure for cancer is somewhere in the Amazon. We just need to, go out and discover it with it before it burns, right? So, I mean, I think the same is true with existing artificial life. There's a lot more interesting stuff in there that has commercial applications. It's just a matter of, as people have with various components, take them and run with them in a variety of different directions and see what comes out of that. And that is certainly what I would say to, folks in their late teens, early 20s that are listening to this, is that some of these building blocks are still there, haven't been explored, haven't been commercialized. And this is certainly what interests me going forward. I mean, I think it's fun what has become hyper-optimized and, you can now run on your handheld device really quickly without burning up a bunch of power. I mean, that's generally smart and fascinating, but there's a bunch of other stuff that hasn't happened to yet, and I think is still very interesting, and that's what keeps me working on my stuff. So
I mean, talking about the simulation structure then for stuff like ApeSDK, what parts, because obviously you've got, weather modeling and agent modeling and a whole lot of different systems. Which of those, just out of curiosity, which of those seem to stick out as opposed to like what people are doing in deep learning at the moment?
Well, I'm fascinated by complexity and evolving narrative. So, I mean, I think there's a lot of really simple language analysis stuff in deep learning currently. But I think what interests me is the kind of interconnected points. I did a talk which is in the Biota audio associated with crime fighting, let's just call them simulated apes. And I think that stuff is still relatively untouched. I know there's a bunch of work currently that's going into contract law associated with analyzing the validity of non-disclosure contracts, for example. But no one is using this technology yet associated with, court transcripts and identifying multi-participant court cases where there is actual spatial distinction in the information that's being presented as a means of dramatically analysing these kind of cases. I talked while I was in Australia. I have a luxury occasionally in Australia of meeting people that are pretty at the top of their game. And I met someone who works in the juvenile justice system, but in the psychiatric aspect of that. And I was talking about the notion of crime fighting simulated apes and what that meant. And she said, well, immediately she works with juveniles that have long-standing court histories. We've had people that have participated in the Biota podcast historically that have talked about this, but the ability just to look at narrative and identify mental health issues, I think, is incredibly powerful. I mean, there are many different aspects of this thing, but let's talk about the ApeSDK specifically. I think the narrative stuff is something that still fascinates me. I talked to Bob Mottram after I worked on libdeep. He worked on another project which was originally called Monkey Mind, then he called it Lib Theatre of the Mind, which is a rewriting of aspects of the ApeSDK around the internal agent modeling interaction. I think there's still, that's still an interesting point. I think the nature of organic external simulations is still very poorly understood. We talked with a fellow called, he was with the Santa Fe Institute, Stephen Gurin, about simulation science. And I think there's still a lot of really interesting complexity modeling, which is just implicit in these simulations, which could be useful in mathematics and physics. So,
what's an example of that?
An example of that is that in certain aspects of multidimensional calculus, there's a language that describes, things like curls and grads and this kind of stuff, where you need to have a language associated with these mathematical properties. Well, when you have a variety of agents, the agent interaction produces similar interactive things which need mathematical terms so that they can go back into complexity theory and solve, various problems in these academic disciplines. So I think this is stuff that interests me, but I'm not in the academic field associated with this thing. It's just something that I've seen through observation, talked with obviously Stephen Gurin about a long time ago. But it's always resonated with me that aspect is still there, that we still lack the mathematical language, which we get in part through experience and part through running these simulations. But this could, lead back into something and within that, the problems that are going to be solved are incredibly useful in economics, for example. So, this is another area where potentially, these tinkerings could actually give something back. And historically, particularly when I was in Las Vegas, I had connections who were, I guess you call them corporate economists. I don't even know what we'll call them, like speculative financiers, for example, that were fascinated by how aspects of artificial life could be used in explaining complexity in financial simulations. And I think to a certain extent, Justin Lyon, who was an interesting character and a somewhat polarizing character who I interviewed early on through this, has actually made a business out of that in the UK. So his business, Simudyne, was funded for a number of years by Barclays, the bank in the UK. And he does basically artificial life simulation financial modeling. And I don't know
that's
the depth
interesting.
that it gets into, but I think that's an area that, the artificial life community, just as a means of like funding and developing, that interests me as well. So yeah, I think there's lots of different areas. It's just a matter of getting a new generation interested and involved.
Yeah, I mean, I think it's a very complex thing to mash all these different simulations together. I think in most software, I sort of had this realization a few years ago after having worked on a sort of 3D package that there's just some software that is vastly different than other software. Like for some reason, that never really occurred to me. But then I found this sort of hierarchy of software complexity, and I think the number one thing is like either operating systems or 3D packages, and then like number two is like compilers, and then it sort of kind of goes down and down. And I think what's interesting is that I think most software jobs tend to be quite restricted to doing a tool or a thing that is relatively focused in scope. There might be some system engineering, but it's usually pretty confined. And it's not until you get to things like operating systems that you're really, mostly doing systems work, and the programming is sort of less of a focus, less about potentially making it run fast, more kind of architecting it to run fast or to be flexible or whatever your goals are. So I'm curious if, since you've had a lot of experience in that, have you found like what's the main thing that you've stumbled on with ApeSDK that hasn't been maybe obvious to other people writing normal software?
I mean, what I find is certainly there's a good group of folk, particularly, now Google, but historically Apple as well, that just say to me, like, kudos for maintaining this thing for such a long length of time. Because maintaining relatively complex, some would say unintelligible, I would argue that, but relatively complex software for a long period of time through a variety of changes is difficult. I mean, the nature of operating systems and all this kind of stuff has changed dramatically from when I started. So I think the idea of maintaining software with a certain degree of complexity and maybe a certain degree of, I don't know, I wouldn't want to say impenetrability, but, it has something which is distinct and many people can focus on the novelty aspect of it, I think is fascinating. My evolving relationship with this thing comes through an ability to put ideas down, pick them up, put them down, pick them up. And for example, the iOS app aspect of this thing, for a few months I wasn't able to work on it. I came back to it and I was like, I don't really like this part. I don't really like that part. The visualization's not right here. I need to work on this. Certain aspects of the simulation have changed. I think to a certain extent it has, I joke about this, but it is very much like gardening. It is very much like a hobby that you return to. But through that, the ability not to predict how the software is going to behave is something that I find really fascinating. The fact that I can have a kind of novel relationship with this thing. I'm just like, okay, so let's see what happens when I put noble apes in an urban environment. Let's see what happens to this thing. Okay, well, we've got hard surfaces. Okay, well, that's interesting. Oh, that's interesting. Well, now I need to start debugging this because I'm not really understanding what's going on here. Well, now I need to create a new interface to understand, what's happening here. Oh, that's interesting. And then, so, I think the nature of the software as being something which keeps me interested as I throw new problems to it, or, potentially if I buy a Roomba-esque open source hackable thing, put the ApeSDK on there, see what happens with that. I think it has an existence which is in many ways completely removed from me. It's one of the reasons I feel so passionately about maintaining it, irrespective of, what third-party comedians and other things might happen, is that it has it is an entity which is independent from me fundamentally. And what I saw when people use it, like when Bob Mottram picked it up, for example, was absolutely fascinating because someone else gets to play with it and see, strange stuff and add to it and, become fascinated by, let's create a simulation of the theater of the mind within this thing and let's see what happens with the hat. And, so, for me, it's a multi-level thing. It's something that I obviously get enjoyment out of, but it's not just a single kind of enjoyment. And then, of course, you've got the Apple's no longer supporting OpenGL. I've got to rewrite all of this. Or, that thing's broken in a crazy way. Or, as it happened, after Apple, forced me into implementing Metal, they broke Metal. So it's like, okay. Well, and you've experienced this recently, right? This has been your experience too. you start playing with this thing, you start getting into it. Oh, wait, I've broken the compiler.
Yeah, I mean, that's a whole... If you need Vulkan startup code, by the way, I've got like a basic sane example that is, GL-esque, but a bit modernized. So anyway, but do you have any kind of rules of thumb for when you add these new systems in order not to like topple the complex system that you already have? Like, do you just kind of hack in new stuff? Like you said, urban environments, you just like plonk that right in the middle of your code base, or do you have like some
it needs to be
methods?
Robust, right? I mean, look, everything, the nature of this thing is calling it an ApeSDK now is actually pretty fair because there's a shim that makes it into, the simulated ape thing, which is what, runs on a Mac or Windows machine. Then you've got a shim that makes it into the ApeSim, which is what runs on iOS. Then you have a shim that makes it into, simulated urban environment, which is the urban environment. You have a shim that, makes it run in a pitched battle warfare simulation. You have a shim that makes it into a planetary simulation, but it's all based on the ApeSDK. And what's interesting in the ApeSDK actually is that there are now components which easily exist in other languages. Like there's a standard JSON object handling component, which obviously exists in a bunch of other languages. So it's easy to then, get interfaces, say, well, I'd like this to be, a server that produces HTTP responses and pumps out JSON. Well, then you can connect it up to something else. So, I mean, my view is the more stuff that uses the ApeSDK, the more robust it becomes. And when I find stupid bottlenecks in there, I have to deal with them in a very practical way. So, the notion...
So you don't do any kind of architecture up front. You let the uses of it sort of drive where...
I mean, you're always doing some architecture around it. You always want something that's going to not really... I mean, when you have as many, different interfaces and different components using it, it needs to be robust anyway. So it needs to be architected in some regard. I mean, certainly when I moved to the client-server architecture, I had to do some internal rewiring, particularly associated with, the relationships of information and information changes and how this was going to work, atomically in one fashion and also, in vastly parallel ways otherwise. And you break out, this is the time component, this is the weather component, they can run separately. You're always doing these, architecture bits and pieces, but the main thing is just getting the code working in many different ways as possible.
Have you found, I mean, you mentioned time, interestingly, like one of the core questions that I keep coming back to with every different A-Life sim that I've written is, what's my model of sort of time and space? Like, is it discrete time or is it analog time? Is it discrete space or analog space, or is it a mixture? And do you have a broad preference, or do you...
I've always used discrete time.
Do you have any gotchas there?
I've always used discrete time, but I mean, my view is that I've often toyed with the idea of rewriting it in terms of just event space. And I think event space actually, and I've talked to a wide variety of folk in this podcast historically about rewriting event-based simulation with the view that there's a lot of interesting, like once you get into event-based simulation, you could probably scale and distribute it a lot easier. In what I have done, because I have a physics that, I have written and this kind of stuff, obviously discrete time is pretty central to that, but time is just a module. You could pull it out. And certainly, if you look at the way Bob Mottram writes code, he doesn't require discrete time. All his stuff, theater of the mind, everything, is based solely on events. So you don't need a core time, discrete time simulation to run Bob's stuff. You just need to pass events around.
And what about space? And I haven't dug enough into ApeSDK, but do you have like some underlying grid, or do you do the whole thing in analog and then use grid for acceleration? Or?
Grid is used for certain things. So, for example, a biology is based on a grid, but it's based on a noise map grid, and which means that you only need to calculate it when you interact with it. I mean, it kind of exists in it was like Schrodinger's cat in one regard. I mean, it's all quantum mechanics in terms of Schrodinger stuff. So the notion is you only need to calculate the stuff that you're directly interacting with, and the rest of it continues to run and maintain various, biological principles. So when you interrogate it next, it's in a different ordered state. So I think those ideas early on that gelled with me with quantum mechanics, if I'm going to make a biological simulation, it needs to be based on quantum mechanics because I don't want to be doing the calculations everywhere. but I want to be doing the calculations when I interact with the various parts of the simulation. So, I mean, that was the nature of the biology early on in the ApeSDK, and it's stuck there, and it's worked actually remarkably well because, I mean, through that, as you have moving sunlight, the interaction of time, the wave functions that interact with that, you get really interesting biological properties that come back but don't have to be calculated at every point at every time.
So you don't, so you sort of procedurally generate, statelessly the entire weather and temperature and sun.
No, the weather is different. So the weather is done in a cell-based simulation, but the sunlight interaction and the weather calculation back into the biological system is all done with quantum mechanics. So the underlying wave functions exist there, and over time they evolve as the sun moves and the rain falls and all these other things go on. But it means that you don't have to be doing those calculations at all times. You just have to be doing the calculations when you interact with them. And they evolve over time. Okay. And you can map what's happening without question. I mean, I did it early on with the simulation. It's just, let's show what the ant populations are doing over time as the rain falls and all these things take place. I mean, does it look biological? It looks perfectly biological. It looks wonderful, in fact. I've done those calculations in advance. Now, both Bob and I have pulled out the quantum mechanics biological simulation and put in traditional predator-prey models. We've put in kind of A-life cellular automata models. We've put in a wide variety of models to see, well, can we switch out the biology? What happens when we switch out the biology? What happens if we actually track, grass insect populations at an individual 10 by 10 centimeter squares throughout the simulation? Yeah. I mean, we've done it all. So the fact that these simulations can be added and removed is very useful over time, because if you get bored with this and you just want to do traditional, like I think they're called Lagrangian predator-prey models, you could do those traditional Lagrangian predator-prey models. It's all available to you. The beauty of this environment is the ability that you can just switch stuff out. And as you find it interesting, I mean, Bob was fascinated by how grass grew in the simulation for a long period of time. He swapped out the quantum mechanics simulation and put in like a grass growing simulation where the apes and the ants and all the critters and birds and what have you preyed on the grass, and he did individual calculations and it looked beautiful. But honestly, it wasn't, I mean, it was comparable from my perspective to what we got out with the quantum mechanical model. So, yeah.
Interestingly, I just saw an article about somebody who's been studying the predator-prey models, and apparently they've been able to replicate. I hadn't known this, but apparently they haven't been able to replicate, predator-prey cycles in the lab for very long. Like they can get like 2 or 3 generations and then things die out, but they just replicated something like 500 to 50 cycles or something.
Well, the kind of interested complexity. I mean, the trick is the more things that you throw in there. I wrote a simulation in 97 for high school students called Ecosim, I think it was called at the time. I think this might still be available on SourceForge. And it was basically a kind of hierarchical tree, but with a variety of predator-preys. I think there were about 20 of them total. You could control their growth rates and their prediction rates, so their various things that they preyed on. And then you ran the simulation over time, and you could see how long you could get things to go until things went extinct. Well, actually, you could get quite good through this, and you'd start off with maybe, 2 prey, 1 predator, 3 prey, 2 predators hierarchy. You'd expand it. You'd eventually get used to how to do this. And you realized as there was more complexity, there was actually greater stability if you got some of the factors right early on. So I think what I find is that what I found through this was the more complexity you have in your predator-prey models, which, funnily enough, now, if you look at when we were in Australia, we went to a dingo sanctuary. I'm in 2 minds about dingo sanctuaries, but I do like dingoes. And if you have to go to a dingo sanctuary to spend time with dingoes, I'll go to a dingo sanctuary. Well, the fellow in the dingo sanctuary was talking a lot about the wolf models of North America. I have a coworker that's also obsessed with the wolf models of North America, associated with how to explain like wolf populations and how they grow and how they have, how many litters or what have you, and the impact that they have on ecosystems. And I think, by recollection, it's not Yosemite. One of the national parks has this long 20-year wolf reintroduction, thing that you regularly read about, where actually when you introduce wolves into an ecosystem, the ecosystem becomes amazing, right? You need these higher order smart predators.
Yeah, I remember I read an article, I think it was Yosemite, where they the wolves, got hunted to death or something or other, and then all this ecosystem collapsed, and then they reintroduced the wolves to maintain the population of something or other. And then in 10 years, rivers fixed themselves and the bears came back, and the berries started all these knock-on effects. When you read through it, sort of makes sense because the wolves ate this and that thing stopped eating the other thing. And then
that's a predator-prey simulation, right? That's a real life predator-prey simulation. So I think, I find predator-prey simulations fascinating. I think if more people understood predator-prey simulations from an early age, this is why I wanted to create it for high school students, then, ecology would be a different thing. It would certainly be in front of consciousness for a majority of the population. So, yeah.
Well, it's interesting that most of the time they're taught with just, sheep and wolves or rabbits and this, and it's usually two things. And people don't really, it feels like, oh, maybe then you add the sheep eating the grass, and that's kind of where people stop. But it's very rare you hear about somebody doing 20 different animals, because I think people assume, okay, well, it's just more of the same. But I think they miss this whole idea.
Yeah.
It's not, right? It's in the same way, I guess deep neural nets are not quite the same as shallow neural nets, maybe sort of functionally to some extent. But, the project that I was asking you about for the parallelism is actually, funnily enough, I was trying to do an ecosystem sim. Was your one simulating stuff moving kind of spatially, or was it more trying to simulate rates?
It was just a numerical simulation. That was the remit. Okay. So it was very simple. It was notion of population growth and predation around interactions on a relatively, it was complex because there were a lot of species, but it was a hierarchical tree. So within that, I think there were two first order top predators, and it went down to the grass and the fish. And the fish were a constant because it was simulating an island. So I made the fish a constant, but you could change the relative constantness of the fish. So those that fished on the outskirts, but it wasn't in any way spatial. It was purely based on rates. And even just based on rates, you got beautiful, oscillating complexity where you'd be like, this population's coming, this population's going down. You got the predation. You could see it all in real time. And I think part of it was also doing the real time stepping. You could just run the simulation and see, okay. And then you'd make a tweak, and then you'd run the simulation again. You'd say, okay. Then you make another tweak, you run the simulation again. You make another tweak, you run the simulation again. So over time, in an order of an hour, say, you had run the simulation maybe 100 times, and you started to get a sense of, these amphibians and these lizards are they prey on things, but they're also preyed upon by other things, and they're actually interesting kind of buffers. And then you start to see vegetation and trees, and what are these impacts that these things change on a variety. You see flow throughs, you see what I would call kind of call response simulation curves, where something rises, something responds, something falls, something. So you get these beautiful interactions, which you can see visually. It's graphically, but you see as you move sliders, and it's an ongoing experimentation. And I think while being relatively simple, it certainly conveyed the idea that the more complexity you have in an ecosystem, even with fixed rates. Now, the wolves, in the example we discussed, the rates aren't fixed, right? The birth rate actually is variable, and is variable based on interactive factors, which gets really interesting. And I wasn't simulating that with Ecosim, but it'd be relatively easy to add that aspect to simulation. I should point this out as well. The first programming I did early on, when I was probably about 14, first commercial programming I did was for an organization called the Commonwealth Science and Industry Research Organization, the CSIRO, and it was looking at riverbank interactions, both with regards to water flow, with regards to, various kinds of algae, water plants, but also with amphibians and things that birds that preyed on the amphibians. So relatively complex ecosystems that existed in waterways. And that was all done through Fortran, I think. And it was all done with relatively simple mathematics. Now, there was various flow theory and other things, but again, layered complexity in simulation, but done with very simple tools. I think all these things should become part of the kit of the early artificial life developer to get a sense of, if you want to create an artificial life environment, there are these existing hypotheses. At the time, obviously, quantum mechanics wasn't necessarily a hypothesis for how to do biological simulation. But I thought, well, I'm interested in quantum mechanics. I'm studying it. This looks like it kind of work well on the biology. Let's put these two things together. So, I mean, I think there needs to be a freedom to hybridize, for want of a better term. I mean, Bob very much took textbook stuff. I mean, he certainly took stuff from MIT, for example, associated with social graphs and social interaction, numerical social interaction, and he just implemented that. He implemented a blood flow model that he just picked up for academic papers. I mean, so there are two extremes. You can take from lots of existing work and just kind of stick it together like a kind of Frankensteinian simulation, or you can take aspects that are not in academic work and try your own stuff. I mean, I don't think there's a right answer to do this, although maybe the academics would say, no, the right answer is to take from academic works and put it together in some Frankenstein. But, I think what's interesting here is just that there are still, many, many possibilities for exploration that folks can delve into.
Yeah, and I think the learning aspect, like you said, is key. Even if, like you said, if it's just lines or a graph, that the fact that it comes across that, in some sense, having less graphics is better in that it sort of makes the idea even more clear, that it's less about just looking at stuff visually. Because even if you were looking at these things visually, you probably would still want the graphs to give you an overview, because it's hard to follow things visually. Like, when I did the beehive simulation, you can't see what's going on with 10,000 bees in any sensible way. So you start plotting these things, and it becomes somewhat annoying, because you're like, oh, I made this whole simulation, and now all I'm doing is just like looking at statistics and graphs about it, because it's completely imparsable, in the same way that, real biological field work is often just all about taking lots of data points and looking at stuff. So I think, in a way, it's actually, if the goal is education rather than entertainment, for example, then having it just be numbers is better. I mean, I came into, like, it's great to hear you say that adding more makes it more stable, provided you kind of do it right. Because one of the reasons I was trying to do it is I was trying to make these little artificial life games, and the common problem you get is, with just, sheep and wolves or whatever, you try to make something and it's very easy to boom or bust it. Mm-hmm. And it doesn't make for a very fun game, because, you can't do much as a user. It just kind of dies out, or it busts out of control. And so I was thinking of ways to stabilize the stuff. And so I had some ways of stabilizing it in hacky ways, some ways of doing it a bit more principled. And then this new thing I wanted to try was to add vastly more species, just sort of.
Yep, that's the way to do it.
Actually, as a therapeutic, as like a therapeutic device. So I was like, I'll just sit here and just code random animals for fun,
Exactly.
Just knock them out, just do a dozen or 2 dozen. So I thought maybe that'll do something, maybe just by throwing raw complexity at. So it's good to know that that's doable.
That's actually the solution. It's not just doable, it's the solution.
That's great. I mean, then that could be an interesting game experience in itself, is like realizing that as you add more stuff. Yeah, it's a great learning for somebody young, right? Like,
Will Wright's already done this, right? I mean, let's acknowledge Will Wright here. Like, there have been people that have already come up with this idea. This isn't rocket science, and I think.
But what game did he do? Lots of species. I mean, Spore didn't really.
Well, look at SimCity.
Work on that level.
Look at SimCity.
Well, yeah. So you have to transfer from SimCity to like ecosystems, but yeah. As in, like, mentally say, and therefore,
yes. Well,
wolves are like that too.
Wolves are like industries and politicians, and
right.
Wolves are certainly like politicians.
No, but of course,
yeah. Well, Anton, I think we've covered many different bases here. We've probably whetted the appetites of our listeners for 2020 onwards and upwards with whatever this podcast is going to be called. And I mean, certainly, look, I'd encourage folks to get in contact, and let's have multi-dimensional jamming sessions with a wide variety of folk about this stuff. But also, it's been really fun for the past year having the chance to chat with you periodically, and certainly coming out and seeing you in Berkeley as well, Anton. So thank you very much. In terms of your A-Life get-togethers and in terms of that kind of stuff, are you still doing that? Have you been able to, bring folks together recently?
I haven't recently. We tried to get together, and it sort of fizzled out because everybody was busy in the summer, and then I got busy, and so I need to put my organizer hat back on and try and do it. We had a goal of doing it once every few months, but apparently even that was too ambitious. So maybe once a year now is the new target. So we'll see.
Terrific. Anton, it's been a pleasure as always. Let's not wait It's been about 6 months since we last spoke, hasn't it? It's been too long, anyway. Let's not wait too long.
Yeah, thanks for having me on.
Yeah, always a pleasure, Anton. I'll talk to you soon. Take care.
Take care.